class, welcome back again. Today's lesson is about gravitational potential. This is class by Raj, teaching for Physics Form 6, Semester 1. The learning outcome for today's lesson is to define potential at a point in a gravitational field, to derive and use the formula for potential and use the formula for potential energy. Before we go into the understanding of a gravitational potential energy, let's understand what is the work energy theorem. It's a theorem that you are very familiar with when you were in your Form 4. Generally, the work energy theorem says that the work done on a system equals the increase in its mechanical energy. That means the work done on a system is equals the increase in its mechanical energy of the system. And work done by a system equals the decrease in its mechanical energy of the system. Now, when we talk about mechanical energy class, what do we understand? Mechanical energy are energy that is consist of either potential energy or kinetic energy, or it can also consist of both. But when we're going to apply the concept of work energy theorem in gravitational, we have to change it in a way for better understanding and be specified in this particular chapter. In gravitational, the work done on a system means the work done on the gravitational force. In the gravitational, usually the system is the Earth. So when work is done on a system, that means the work is done on the gravitational force. When work is done on the gravitational force, according to the work energy theorem, it says it increases its mechanical energy. So therefore, it also increases its or gain. We can also use the word gain, and the mechanical energy that we are talking under the gravitational energy will be the potential energy. If is work done by the gravitational force refers to the work by a system. And if the system is Earth, so work done by a system, work done by the Earth is work done by the gravitational force that is on the Earth. And this has caused the decrease or loss in its mechanical energy, which is specified to the potential energy in this particular topic. The gravitational potential, which is a V, at a point in a gravitational field is defined as the work done per unit mass. Work done per unit mass to bring a body from infinity to point P. So you see class, when you bring a body from infinity to point P, it means the work is done by the system. When work is done by the system, that means that the work is done by the gravitational force. And this is according to the work energy theorem. When work is done by the gravitational force or work is done by the system, its potential will decrease. Its potential energy will decreases. When its potential decreases, then the potential value is a negative, which is V equals to negative Gm over R square. The gravitational potential energy of a body at a point P in a gravitational field is defined as work done to bring a body from infinity to P. Work done to bring a body from infinity to P. Now, when a body is brought from infinity to point P, then the work is done by the system. When work is done by the system, therefore we can say work is done by the gravitational force. When work is done by the gravitational force, then we can say that its potential energy decreases by using our work energy theorem. When its potential energy is decreasing, then the potential energy is negative. Therefore, you get your formula U equals to negative GMM over R.
Look on the concept of gravitational potential. Now here, if you see here in this diagram, I have Earth, okay, which is the mass is capital M, all right, and then I have um, this small mass here, okay, is another planet with a small mass here. Okay, now this small mass M is inside the gravitational field of the Earth. So what happened is there will be a gravitational force that will act on the planet, okay, which will be towards the center of the Earth. There will be a gravitational force. So F is equals to, according to the concept of universal Newton law of universal gravitational, F equals to negative G M over, okay, so from here to here is X, so it will be X squared. Okay, so that is the first one. Then the second one is, I'm going to write down the concept here. We're going to look at the work done, okay, the work done to move the body, okay, the work done to move a body a small distance dx, okay, the work done to move the body a small distance dx, okay. So we know from the definition, okay, work done is W is equals to Fs. So in this case, W is equals to F. Your S, okay, will be negative dx. Now why negative? Because it is the small distance is in the opposite direction towards the increment of x. So x is increasing in this direction, right? So dx is in the direction which is from here to here, which is what we call this is in a small distance, okay, from here to here. So it's like a from this position to this position, okay, your dx. All right, so it's from this position to this position, so your negative dx is in the direction which is opposite to the direction of increasing x, okay. And then we substitute F, which is negative G M over x square, and then we get negative dx. All right, okay, then we solve this, we get G M over x square. All right, another concept is we're going to look at, okay, now when this mass is moved from one distance to another distance in the gravitational field, we go back to the concept of work energy theorem, okay. So I'm going to write here the concept of work energy theorem, number 2, work energy theorem. Okay, according to the work energy theorem, it says what? First thing is work is done by the gravitational force, because the gravitational force is towards the center of the earth. So to move from this position to this position, which is a small distance of dx, so work is done by the gravitational force. Number 1, work is done by the gravitational force, Fg, okay, the first one. The second one, we can say also, we can describe also, work is done by the system, Work is done by the system. It is a system the system is the earth, yeah. It is by the system that is doing the work to bring the mass of m from one position to another position in the gravitational field. So work is done by the system. Okay, according to the work energy theorem, when work is done by the system, what will happen? It will decrease in its mechanical energy. It will decrease in its mechanical energy. Now, when we talk about mechanical energy is kinetic energy or potential energy, or you can plus both kinetic and potential energy. So in this case, the work is done to bring from one position to another position. So it is involving potential energy. It's involving what? It's involving potential energy. So its decrease is in its potential energy. Sometimes we don't use the word decrease, also okay. We can also use the word lost in its mechanical energy, which is the potential energy. Okay, all right, so let's look at number 3. Okay, let's look at number 3. All right, so work done. When we talk about work done is actually referring to delta U according to the work energy theorem. Okay, so here U. Alright, so let's look at work done to bring a body from infinity. Okay, now the work done. Let's look at number 3. Yeah, number 3. The work done to move the body from infinity to distance r. Okay, to distance r, which is point P. Okay, so let's assume this is some point P here. Okay, point P here. Okay, this is number 3. Yeah, point P here, which is a distance r. Okay, which is a distance r from the center of the earth. So what is the work done to bring a body of mass m, the same mass m, from infinity, okay, same mass m, from infinity to point P. We're going to bring from here to point P. Okay, we're going to bring the body from infinity to point P. Okay, so we know, all right, U. Okay, just a minute. U, work done is what? Work done, W is equals to delta U. Okay, so let's look at that. U is equals to integrate from infinity to point P, which is R, from the center of the earth. Okay, so times with du. Okay, so now we take R infinity, and what is du? Du, according to here, du is what? Gmm over x square. Now, why did I replace du is gmm over x square? Because w is equals to what? W is equals to du or delta u. Okay, so w is equals to du because work done is du. Okay, change in energy. Okay, all right, du or delta u. Okay, so here I put du, which is du is equals to gmm over x square. I substitute this inside here. Okay, and dx, and then when I integrate this, I will get negative gmm over x. Okay, r infinite. Okay, so then when I substitute this infinite and r inside here, I will get negative gmm over r plus with infinity is 0. Now, why infinity is u in infinity is 0? Because u at infinity is always 0. So when I substitute gmm over x, which is x is infinite, I will get 0. So I will get my answer is u is equals to negative gmm over r. Okay, so if you realize that, okay, this thing uh, will consistent with the concept of work energy theorem. How it's consistent is when a mass is brought from infinity to point R, so work is done by the gravitational force, work is done by the system, it will decrease it in its mechanical energy, which is the potential energy. So that means you will get your potential energy here is negative. Okay, so that's why it is consistent there. Okay, another concept is, which I'm going to write with the pink color pen, which is the concept says that gravitational potential. Okay, so we know B is equals to U over M. Okay, so therefore we substitute the side inside here, we get V is equals to U will be negative G M over R. Okay, so this is the formula of gravitational potential. This one is gravitational potential energy. Okay, all right, so that is the concept of gravitational potential. So to describe the gravitational potential, we can divide into three: the first understanding, the second understanding, the third understanding. Okay, first is the small distance dx, and the next will be from infinity to point P, which is the distance r to the center of the earth, from the center of the earth, and then we get the formula for u equals to negative gmm over r. Okay, so that's all class. Thank you. Another example here, the mass of a planet is 5 times 10 to the power of 24 kg. Okay, the mass of a planet is 5 times 10 to the power of 24 kg, and its radius is 6 times 10 to the power of 8. Okay, so the mass of this planet is 5 times 10 to the power of 24 kg. Okay, and its radius from the center. So be careful with the word radius and height. Okay, so the radius is 6 times 10 to the power of 8. I just simply put a figure of earth. Okay, so this is not telling that it's referring to earth. Okay, so I'm just going to put there the mass of a planet. Okay, and its radius is 6 times 10 to the power of 8. What is the energy required to bring a mass of 2 kg? So this is a 2 kg, okay, from the surface of the planet to outer space. Okay, so from the surface of the planet to outer space. Outer space means infinity. Okay, now we know around here, okay, let me just take a pencil. We know around the planet there is a gravitational force which is towards the center of the earth. Okay, so I'm just going to roughly draw class. Okay, okay, so here when you have this, the planet is in the gravitational field of the earth. So what is the first concept, class? So work is done on the gravitational force. Number one, work is done what? Work is done on the gravitational force. Number two, work is done on the gravitational force because the direction of the field is in this direction. So now you want to bring the mass from this position to a infinite. Okay, so you have to do work on the gravitational force. So we can also say the word work is done on the system. Okay, we can also say work is done on the system. Now, according to work energy theorem, okay, work energy theorem, work is done on the system, increase the mechanical energy. Okay, increase the mechanical energy. Now here the work mechanical energy is from one position to another position. So it's specified to potential energy. So it increase the potential energy. Okay, so we know from the concept is W is equals to what? W is equals to delta U. We know our delta U is positive value. Because why? The word increase. Increase can also be mean gain. Okay, gain. So you gain. Decrease means loss. Okay. So delta U. Now the thing is, the question asks, what is the energy required to bring? The energy required. So energy is specified here is potential energy. Because it is to bring from one position to another position. So it's referred to potential energy. So in this case, delta U is equals to final minus position, final minus initial. So it was initial here and then it is brought to infinite. So you want to find the change of energy. So you take final U infinity, you minus with U R. Okay, I'm going to just put UR here. U infinite minus with UR. Okay, so delta U is equals to U infinite minus UR. Always take final minus initial. Okay, so final. We know U infinite. You have to know this is equals to 0. Potential in infinity is 0. Okay, so I put 0 minus. Okay, so the formula says negative GMM over R. Okay, so therefore I get what? I get GMM over R. So G is our universal gravitational constant. Okay, it will be 6.67 times 10 to the power of negative 11. Your M is this, the big mass. Okay, which will be 5 times 10 to the power of 24. And then your small m will be 2 kg. And then your distance will be 6 times 10 to the power of 8. So if you solve this class, okay, if you solve this, okay, let me see, your answer you will get around 1.11, I think 1.11 times 10 to the power of 6 joules. So your value is positive value. So positive value shows there is a gain. Okay, it's a gain in the potential energy. Gain in the potential energy. So it will show in your calculation, your final answer. Okay, alright, so that is how we use work energy theorem to solve questions that is regarding potential energies and also work. Okay, work done. Alright, so that's it. Change in the gravitational potential energy. Okay, we have a planet here. Okay, mass is capital M, and then the mass of this mass here is small m. Okay, alright. Okay, the radius will be R. So this is at the surface. Okay, alright. So now this planet, alright, this body or this body of a mass m on the surface of the planet has its gravitational potential energy U is equals to negative GMM over R. Okay, now this body is raised through a small height. Okay, it's raised from here through a small height. Okay, which is, I'm going to just draw here, small height. From here, delta R. Okay, it's somewhere here, raised through a small height of delta R. So the U here, okay, U, okay, R plus delta R will be negative GMM over R plus delta R. This is a small mass m. Okay, from here, what do we know? Okay, first thing, all right. So we know by right the change in potential energy. We know delta U is equals to what? Is equals to the final minus the initial. Okay, this all are just extra way of solving the problem. Okay, so minus with U at the surface, which is UR. I'm going to just put here UR. Okay, all right. There is another way, because we're going to understand the concept of change in gravitational potential energy. So the concept says, number one, okay, work is done on the system. Okay, work is done on the system. The system is the earth. Okay, so you have to do work on the system. That means what? That means work is done on the gravitational force. Work is done on the gravitational force, or okay, work is done on the system, or work is done against the gravitational force, or work is done on the gravitational force. Okay, so according to the work energy theorem, okay, it will increase the potential energy, increase the mechanical energy. So here is move from one position to another position, so it will increase the potential energy. Potential energy increase, also can say the word gain, or gain in the potential energy. So we know that, okay, I'm going to write here, we know W is equals to delta U. Okay, that we know that the change in its gravitational potential energy, delta U, equals the work done. Okay, all right. So therefore we know W. Okay, I'm going to just write like that. Okay, delta U equals to W, just shifting the position. Okay, we know W is equals to Fs. So here F is times with delta R. Okay, why F is involved? Because this system is inside the, this mass is in the gravitational field of the earth, so the direction of F will be in this direction. Okay, towards the center of the earth. Alright, so F times with delta R. Okay, now another concept which I've taught you previously. F is what? The gravitational force is equals to the weight of the body. Okay, the gravitational force is equals to the weight of the body. Okay, so therefore the gravitational force is equals to the weight of the body, so F is equals to mg. Okay, so I substitute mg delta R. Alright, so therefore I get mg delta R. If delta R is equals to h, that means height. Okay, height is h, then I can say delta U is equals to mgh. Okay, delta is equals to what? mgh. Alright, so that is all about change in the gravitational potential energy. So you realize that all the concept is repetitive. Okay, alright.